Okay, so well, I try to be quick. Well, I'm Laura Sebastian. I'm going to present this work that I developed with my colleague Eliseo Marzal, and we all work in the Valencian Research Institute for Artificial Intelligence in Spain. So this is the outline of the talk. First of all, I would like to make a little context of this work because we were working on tourist recommendation. So in the tourist recommendation, we have two parts. First, you have to recommend which are the places that the user prefers to visit. And then the usual thing is to plan these visits into an agenda so that you have to take into account the travel distances and the opening times of the places and things like that. So in this work, what we try to do is to consider some other preferences, like now, for example, when you are very fond of a specific place and a specific museum, for example, maybe you want to visit it longer than other places. Okay, so that's the idea of this work. So first, I'm going to define the basics of this work, and we are working on an orienting problem. Okay, so an orienting problem is just a problem where you have some nodes, and you have to select which of them to visit and to order in a sequence. If you want to compute more than one route, then you are in the team orienting problem, and this is a very simple example. Then if you add time windows, as it happens when you are trying to compute a plan for visiting a city, then you move to the team orienting problem with time windows. In that case, the order of the scheduled visits depend not only in the travel distance between these places, but also in the time windows, because you cannot visit a place that is close, obviously. So on the other hand, there is another type of orienting problem, which is called the orienting problem with variable profit, where the idea is that you collect more profit when you stay longer in a certain place. Okay, so if you visit a node longer, then you get more profit, or if you visit it several times. Okay, so the idea of our work is to join these two problems so that we came up with the team orienting problem with time windows and variable profit. Not very original, the name. So this problem can be applied, for example, for the routing of reconnaissance vehicles, because in that case, you have to visit some places, and if you stay longer, then you can get more information about that place, okay? And also, of course, to the tourist trip design problem, and I'm going to show you a little example. So imagine that you are in Sofia, and you want to visit some places that we are going to do this afternoon. So here you have the hotel, for example, the Astoria Hotel, and then you want to visit those places. Assume that they are separate, or their distance is only 5 time units, just to make it simple. And the opening hours are the ones in that here. Okay, so these are the opening windows. And this is the profit that you get when you visit each of that places per time unit. Okay, so for example, if you are going to solve the orienting problem with time windows, so you can get this kind of plan where you visit the 4 places for a certain time, let's say 10 time units, and then you have to order them according their time windows. Okay, so in this case, when you have these blank spaces, it means that you don't have any visit there, or you are not moving from one place to another. So that's idle time. Okay. So if we move to the well, in this case, the score of this solution would be 1,900. Then if we move to the orienting problem with variable profits, then in that case, we do not consider the time windows, but we can extend the duration of each visit to increase the profit. I mean, when you stay longer, in this case, in, for example, place number 3, as profit is 100, then if you stay longer, you get more profit for staying in that place. Okay, so in that case, the score of this solution would be 5,000, sorry. So the idea is to combine both things. So for solving the orienting problem with time windows and variable profits, in this case, we have to move visit number 3 till the end because it is open later, and then we can visit place number 2 in first place. Okay, so the idea is to solve problems like this one. And in this case, the score is a little bit lower than in the other case because you have to consider the constraints of the time window. So what we have done is to base our work on the definitions of the mathematical model and the heuristic implementations, as you will see later, on the orienting problem, team orienting problem with time windows. And we have extended these ideas to consider the variable profit. So this is these are the input values for this problem, where we have the set of nodes that we want to visit, the travel time between each pair of places, and for each node we have the profit that you collect when you visit it, then the time window where it is open, and we add the service time interval, which means that you have to visit that place between min d and max d. Okay, so you can extend the visit from min d to max d. The decision variables that we have in this case are the same that's in the team orienting problem, which are the first two, which say that a place is visited after another place, or that a certain place is in one route. Okay, so then we have what is the start of the service at each node, and we add a new decision variable that stores which is the service time at each node, because now this is not a known value, but we have to decide which is the service time at each point. So the goal is to determine en route. It's limited by the maximum time that the user has. Then visit a subset of these nodes within the respective time windows and decide which is the service time at each node in order to maximize the total collected profit. So the maximization function will be this one. Okay, that's saying that we want to maximize for each route the profit for visiting one place for a determined for some time if it's visited in that route. So these are the constraints. I'm not going into the details because, as I'm saying, most of them are based in the orienting problem with time windows, but I only want you to notice that here we have some differences that in the general team orienting problem, the service time is always included in the travel time between places, okay? But in this case, if it is a variable that we have to decide, it's a value that we have to compute, then we have to consider it separated. We have to explicitly put it in the constraint. And also, we have to state that this value has to be between in the interval that we have defined. So we implemented this using, well, our tools. And what we found, it was not very surprising, that it was only able to solve small instances, okay? As it happens when you try to solve this kind of problems with another variants of the team orienting problem. So the idea is that we need a heuristic implementation of this model in order to solve bigger problems. So it is what we did. So we use, we base our algorithm in an iterated local search scheme. This is the general scheme. So we have the construction step, then a local search to improve this first solution, and then we get into a loop trying to improve that solution. Okay, so the first step is a perturbation a step in which one or more nodes will be removed to escape from local optima. Then again, we have a local search step to improve the solution. And then this is the acceptance criterion step, where if the new solution is better, then we update S star, but otherwise we restart S0 with S star after some iterations without improvement. So that's quite the usual thing. Apart from the variables that I said before, we have some other variables that indicate what is the arriving time to a certain node, which is the waiting time that we have to wait in case that place is still closed. And max shift is a value that indicates what is the maximum time that a node can be delayed so that the route is still feasible, okay? So for the construction step, what we do is just to compute a set of feasible candidate nodes, then we select one of them based on the attractiveness of each node, and then we add that node to the route, okay? So, and then we perform this thing again until we don't have more feasible candidate nodes. How to check the feasibility of inserting node J between nodes I and K? So what we have to check is whether the time that we have to add or reduce when a new node is inserted is lower or equal than the time that the waiting time of node in node K plus the quantity of time that this node can be moved can be delayed, okay, in the route. So for example, here we have a route with only one node, which is node 3. And in this case, we can delay this node 5 time units because we have some idle time here. And we have that this node has a waiting time of 25 because of the opening time, okay? So we can check whether we can insert this node in this space here. So we have some calculations, and the thing here is that in order to compute this shift value of this node, we need to know how long it's going to take to visit that place, okay? So this is something that we already don't know, and we have to estimate to know whether we can insert that node in that position. Okay, so how we can estimate DJ? That is the same question as what will be the largest service time to fulfill the shift constraint. Okay, so we need to, because there is another equation here, so here. So we have this equation that we have to fulfill, and this is why, this is how we compute this value, okay? So what we do is just to, well, rewrite these things so that the duration in the service time of this node fulfills the restriction of being in the duration interval, and also we just move these things so as to compute what would be that duration. Okay, so here we can see in the example that after some calculations, the largest service time for this node will be 30. Okay, so here we insert this node in this space that we have here, and we move this node till the end. We don't have that idle time at the end. Okay, we select the largest time, the largest service time, because we want to maximize the profit. Okay, so the idea is to include or to have as less idle time as possible. Then in the local search step, we have three phases. Okay, the first one is in charge of increasing the unused time budget of one or more routes in order to have a space to enlarge the service time of already scheduled nodes, or to add new nodes, or to replace existing nodes with new nodes. Okay, so this step and this one are already defined in the algorithm for solving the orienting problem with time windows, and this is the step where we have add in order to consider the variable profit. So the idea is very simple. We have to find which are the nodes whose service time can be enlarged, and then we select the node with the highest increments in the score. So if we have this situation, then all nodes can be enlarged because all nodes have this max shift higher than 1. So all of them can be enlarged to fill these blank spaces. And in this case, as number 3 is the one with the highest profit, is the one that is selected, and then we enlarge it as much as possible. Okay. So these are the experiments that we performed with this heuristic implementation. We selected 55 Solomon instances, and we adapted them to this specific problem with variable profit. It was, well, we only add that interval of the service time by saying that the minimum D is the original service time and the max D is original service time plus in this case, arbitrary number, which is 30. Then we implement or we solve 2 baselines, which is the orienting problem with time windows, with min D, which is the original problem, and then with max D. Okay, and we compute the average value of 10 runs, and then we also show here the maximum value of 10 runs for each of the KPI here that you can see. So for the score, we can see that in all cases except one, our implementation has the best results. And this score is like saying that this is the tourist global satisfaction. Okay, the score is that tourist satisfaction with the plan that we are offering. In case of the number of visits, in all cases, our implementation obtains solutions with a higher number of visits. And in this case, if we make we move it to the tourist problem, this will be the number of different places that the tourists can visit with this solution. Okay, so if we are like more active tourists, we want to visit as many places as possible, and this is the solutions that we are getting with our implementation. And regarding the waiting time, so this is the total spare time that the tourists can have in the plan. Well, it depends. We have some solutions where we have less waiting time, and others where is the max baseline that gets that less waiting time. In that case, it depends on the kind of tourist that we are. If we want to visit a city with in a more relaxing way, maybe we want to have some time to do some shopping or to have a beer or whatever. So maybe solutions with a higher waiting time are preferable or not. So this is something that we are trying to include in our model so that the user can decide which kind of route he prefers, if he prefers a relaxing route with more waiting time or not. Okay. So well, and regarding the execution time, obviously the max baseline gets lower, the lowest values, because it doesn't have to deal with the combinatorial explosion that we have when we have to consider many different durations for each of the nodes, for visiting each of the nodes. So just to conclude, as I was saying that we obtain good results in most of the KPIs that we have tested. We have to perform some other experiments by using different approximations of the max D, because we think that having a higher max D will reduce the flexibility of the max baseline. So we think that in that case, the flexibility of our approximation will be highlighted. And some other things that we want to do is to developing new procedures in order to reduce that execution time. And as I was saying, that we want to include like a custom waiting time in the model so that the user can decide which kind of route he wants to obtain. Okay, so this is it. Thank you very much. Sorry.
Sorry, I just wondered why in the slide with experiments, why number of visits is a decimal number.
Because it is an average. So it's the usual thing is to have an integer number, but as it's an average, that we have that float value.
Antonio, your question.
It's another quick question about the NP-hardness of the problem. I was wondering if it's implied directly by the test P, the traveling salesman problem, or if you make some deeper analysis on the complexity of the problem.
Yeah. It is. Well, I don't know. I don't remember exactly, but yes, it is higher than the team orienting problem with time windows, because we also have that component of the service time that has to be computed.
So it's a special case of a problem that's already NPR.
Yeah.
Yeah. Okay.
Yeah.
Thank you.
Additional constraints. Okay.